Okay, so what we're going to talk about today is how to create or how to calculate radial fits. And what a radial fit is if I have a bearing and a shaft or a pin and a bearing or some two round features that are working together, I need to figure out what type of fit they have. And that could be either a clearance fit, an interference fit, or a transition fit. So what I'm proposing here, whenever you have to create a fit, it's a good idea to create a chart, just like I have here on the screen. And what we're going to have to do is we're going to have to figure out MMC and LMC dimensions for bearings and shafts. Now just remember, MMC is max material condition. That means the most material that's present. And LMC is the least material condition, the least material that's present. Okay, so I'm going to go ahead and figure out these dimensions and fill them into my chart. So if I take a look, I'm always going to start with my bearing because my shaft is going into my bearing, so I want to start with that one first. Okay, so what I'm going to do here, and I'm going to go ahead and I'm going to go back and I'm going to center this. That way it makes it nice and easy to read. My bearing, my maximum material condition bearing is my smallest hole, so I'm going to type in 0.379. My largest hole is my least material bearing, so I'm going to put in 0.381. Now for my shaft, it's the opposite. It's the biggest shaft and then the smallest shaft. So looking at my dimension of 0.375 plus or minus 0.002, I have 0.377 for the MMC, and then I have 0.373 for the LMC. Now I have these set up as underlined because what I'm going to do in my chart is I'm going to basically do a subtraction problem for each of these cases. So if I do my subtraction problem, you can see that what I'm going to end up with here, and I'm going to center this as well, is I'm going to end up with a positive 0.002. And for this one, I'm going to end up with a positive 0.008. Now again, I like to put in signs here because that's going to make determining the type of fit much easier. Okay, so if I take a look here, I've got two positives. If I have two positives, that means I have a clearance fit, which is what I have. If I were to have two negatives, then that would mean I would have an interference fit. If I would have one of each, that means I would have a transition fit. So we're going to do one more as an example. Okay, if we go ahead and I'm going to center all of these here just to make it a little bit easier to read. I'm going to put my underline here so we're all set. Okay, now for my MMC for the shaft in this case, sorry, for the bearing in this case, it's going to be 1.006. My LMC for the bearing in this case is 1.008. For this one, I have for my shaft is 1.007. And for my LMC here, I have 1.003. Okay, and I'm going to make sure that these are underlined. I'll do my math. I have 0.001, and here I have plus 0.005. So since I have one of each, you can see that I have a transition fit. Okay, now for the third case, I went ahead and paused the video and just filled in the numbers here for you so we can go through this a bit faster. For this one, I have a pin of 0.520 plus or minus 0.01 and a bearing of 0.516 plus or minus 0.002. So I went ahead and filled in my dimensions, again, my MMC and LMC of both of them. And I'm going to go ahead and do my math problems here. In this case, I have negative 0.007. And in this case, I have negative 0.001. Now, since I have two negatives here, that means that this one is an interference fit. So again, if both my answers for my problem are positive, I have a clearance fit. If both of them are negative, I have an interference fit. And if I have one of each, that is a transition fit. Okay, in some cases we have to go backwards, meaning we already have the fits and we need to figure out what the dimensions are. So that's what the second part of the video is going to do. So we're going to complete the radial fit design giving clearances and tolerances. So if you take a look at this chart I went ahead and drew some lines on here because it just makes it easier for me, and it'll probably make it easier for you as well. A nominal size, this is basically just an approximation, like it's telling the user that I'm going to have an approximate size of 1 for this assembly. Tolerance, usually I only have one tolerance given, and then for this case it's the shaft. Here I have a minimum clearance and a maximum clearance, and if we remember from our definitions, minimum clearance occurs when we have MMC, and then we have maximum clearance when we have LMC. Okay, then I went ahead and labeled my upper limit shaft, my lower limit shaft with the same labels, my upper limit bearing and my lower limit bearing with the same labels. Now, one thing I do want to make sure I note to you all is that my MMC columns will work together. So if I take a look at this column here, and whatever I put into this column, they're all going to be connected. So that's where my subtraction problem is, or my addition problem. My LMC numbers here is going to work with that column, and this column. Okay, so we want to kind of think about it in the chart that we previously were using. We just turned the chart on its side and organized it a little bit differently into one row. Okay, anytime I move in the direction from left to right, I'm going to be adding numbers. Anytime I move in the direction of right to left, I'm going to be subtracting numbers. So what I'm looking at here is I have to determine which number I want to do first. Now, since I have one of my MMC numbers, I'm going to go ahead and fill in this column first. Okay, so when I'm looking at this, my lower limit bearing minus my upper limit shaft is going to give me my minimum clearance. So this number, whatever that is, minus that number will give me 0.002. So for reversing that, I can say that this number plus that number will give me my lower limit bearing. Okay. Now in this case, I know I have a clearance fit because both of these numbers are positive. So I'm going to go ahead and fill in that number. I have 0.002 plus 1.002, that's going to give me 1.004. Okay, that fills in there. Now, in order to get the other area, this is where the tolerance comes into play. So I have a tolerance for the shaft, so that means I have to fill in this column next. So what I'm going to do, I have my upper limit shaft. I want my smaller shaft, my lower limit shaft. I have to take this tolerance, subtract it twice from that number, and fill in the number here. The reason why I have to subtract it twice is because this is a bilateral tolerance. If I subtract it once, I'll get the middle dimension. If I subtract it twice, I'll get the lower limit dimension. So if I take 1.002, subtract 0.001 times 2, I will get 1.000. Okay? That will give me that number. Now I can finally fill in this last number here in this chart. Okay? What I'm going to do now is, again, I can have my upper limit bearing minus my lower limit shaft will give me my maximum clearance because I'm moving right to left. I'll be subtracting, but I need to move in the other direction, left to right. So I'm going to add the numbers. So I have 0.005 plus my 1.000, and that'll give me 1.005. And then my chart will be completely filled in. Now, if I wanted to, I could go ahead and figure out my nominal size and my dimension. So this would be 1.0045 plus or minus 0.0005 and so on. Okay, so I just want to make sure that you're aware of that. Now, if I scroll down to another chart here, I have a chart that's got 4 rows. And it depends upon like which column I can solve first depends upon what information I have. So again, I can go ahead and draw some lines to help me figure out what exactly is working together. I like to draw those lines here. Minimum clearance is always going to be MMC. Maximum clearance is going to be LMC. Upper limit shaft is MMC. Lower limit is LMC. Upper limit bearing LMC, lower limit bearing is MMC. Okay, now I'm not going to solve these for you here, but just as a reminder, like I said, what we can do is we can use what we have to get the information that we need. Okay, if I look at, we'll do one of these together depending upon the time that I have left. Maybe I can go ahead and get this figured out here for you. So since I have this number here first, I can solve for this using this using the LMC, and this LMC I can solve for this column here. Okay, so what I would do is I would take this number, add it to this number to get that number. Once I have that filled in, I can use my tolerance for my shaft to fill in this other value here, and then finally fill in this. Now, what I want to make sure that you're careful of is that if I go down to this third row, I have the tolerance for the bearing. So that means that I will have to fill in this one second or third. Okay. For this particular row, I have my upper limit bearing minus my lower limit shaft will give me my maximum clearance. So I can basically take this number minus this number to get that number. Okay. Once I have that filled in, I have to do this next because I have my bearing tolerance present. Okay. Okay, so I paused the video and I just went back and filled in some numbers for you so you can see how they work out. Again, I started with this number here. Okay, and I had to go back and figure out this number first. So I used my LMC, added it to my lower limit shaft to get my upper limit bearing. And because I had the bearing tolerance, I had to go find this one next. I took 2 times my bearing tolerance and subtracted that, put my answer here. Now that I have this filled in, I can use this number minus that number to get this one. And that's where I end up. So it really depends upon which numbers you have and which tolerance you have. That's going to determine the order of the cells or the order of the boxes that you'll fill in. Okay, so it just takes practice. And remember, this is laid out very similarly. It's just all in one row rather than two. So I hope that helps. Feel free to go back and pause the video, rewind, and watch it again where you need to.